Well, hey there, guys. Mr. Carlson here again. Let's take a look at another situation. We've got two stick people here, and they are throwing a ball straight up into the air, letting it come back down, and then catching it, and we'll say at the same exact height that it was released. And we're going to assume in this case that the ball, even though I've got it drawn like this, we're going to assume that the ball goes straight up and then comes straight back down. I know that I don't have it drawn exactly like that. I kind of drew it like this just so we could kind of see how the ball speeds up, slows down and then speeds up. But again, we're going to assume that the ball has no horizontal movement to it, goes straight up and then comes straight back down. And let's say in this case, the problem says that the person times how long it takes for the ball to go from this point right here, go up, come back down, and end at the same exact height that it started at. And let's say that the problem tells us that it has a total, we'll say a total hang time. So the amount of time that it's in the air is 5 seconds. That's what we know. And that's it. That's all the problem gives us. It doesn't give us an initial velocity, or anything else. It just tells us that the ball is in the air for a total of 5 seconds. Now remember, for problems like this, the moment that ball leaves his hand and the entire time that it's in the air like this, it is a free-falling object. Even on its way up, it's slowing down, and then on the way back, it's speeding up. That entire time, it has an acceleration of a free-falling object, which is negative 10 meters per second squared. Now, we're also going to make sure we define which direction is negative and which direction is positive. So I'm going to make this direction negative, and going upwards here is going to be positive in this case. So, also linking this to acceleration. So the entire time that the ball is in the air, it has this acceleration. And remember, that's why the ball here is slowing down as it's going up. So as it's going up, it's slowing down because it's accelerating in the negative direction. And remember, we learned that if an object is accelerating opposite the direction of its motion, it has to slow down, right? But then on the back end of this trip, the ball begins to speed up because now it is moving in the same direction that it is accelerating. And anytime the direction of motion and the acceleration are in the same direction, the object is going to speed up. So the acceleration is negative the entire time, which is why it slows down to a stop for a brief second and then speeds up. The other thing that we can infer from this is happening at this moment right here at the top of that trajectory for this ball. What we can assume is that, first of all, the time, so the moment that it hits the top of that is going to be exactly half of the total time, is what we can assume, if this is landing at the same height, which we are assuming that the ball is going to stop at the same height that it was released. So this time right here at the very top of that trajectory is going to be half. So we're going to cut that in half. So we're going to say at that moment right there, that's happening at 2.5 seconds, or in other words, half of the total time that it takes. The other thing that we can assume about that moment right there at the top of that trajectory is that the velocity is going to be, just for a brief millisecond, is going to have 0 meters per second for a velocity right there. So those are two key things that we want to know that are implicit in problems like this. That time right there is halfway, and that at that exact moment, right before it begins to speed up coming down, it's going to have a velocity of 0 meters per second. We're going to need to know that in order to solve these type of problems. So let's say the first part of the problem says, what's the ball's initial velocity then? If it took 5 seconds for that entire trip, what's the initial velocity? How fast was it going when he threw it? So in this case, what I can do is I can, again, using this spot right here, to assume that the velocity at that moment is going to be 0 meters per second, what I can kind of say is that, well, the final velocity right there, if I make that the final velocity, is going to be 0 meters per second. And I also know the acceleration, don't I? I know that the acceleration is going to be negative 10 meters per second squared. And so from there, I also know the time, right? Because it takes 2.5 seconds to get to that point. So now I actually have quite a bit of information, don't I? 2.5 seconds. And so to solve for the initial velocity, I just need this equation right here. We're going to rearrange. Well, actually, let's just plug in the numbers. So my final velocity is 0 meters per second. Initial velocity is what I'm solving for. Plus, the acceleration is negative 10 meters per second squared times the time, which is 2.5 seconds. Let's simplify this. So initial velocity plus, well, actually, let's do minus since it's going to be negative anyways, because that negative right there. So minus 25. And then notice that seconds here is going to cancel out. That's squared, so that squared's going to go away. This seconds is going to go away, so I'm going to be left with meters per second. Meters per second. And this, since this is just 0 over here, to get this initial velocity by itself, I'm just going to add 25 to this side. So that means the initial velocity was 25, positive 25 meters per second, which makes sense. It should be positive because remember we made this direction positive. And so that initial velocity right there, as he throws it up this way, should be a positive 25 meters per second. All right, what about if we ask how high does the ball go? We want to know how high at the peak trajectory right there, what is the distance that it goes? So I'm going to just, well, actually, we got some stuff there, so what I'm going to do is I'm going to make a little room here. We're just going to remember that our initial velocity was positive 25 meters per second. So I'm going to write that over here. Our initial velocity was 25 meters per second. All right, so for part B, we're solving for the distance, or delta x is what we're looking for. Well, I know the initial velocity is 25 meters per second now, and my acceleration is still the same. We're still assuming at this point right here it takes 2.5 seconds, and that it is a final velocity of 0. So let's come over here. The only things that I'm going to be able to use in this case are going to be this middle equation here. And then I could also use this equation right here because I know the initial velocity, I know the final velocity, and I know the acceleration. Let's just, we'll use this equation just for fun. We could just as well have used this one, and that would have been fine, but we'll just choose this equation for now. So we've got delta x is equal to, so let's plug in initial velocity is 25 meters per second times the time, which is 2.5 seconds, plus 1/2 times the acceleration. I'm just going to do that right off the bat. Our acceleration is negative 10, so I'm just going to make that a negative 5 meters per second squared, and then t squared, so 2.5 squared is going to be 6.25. And then again, seconds would also square, so we'd have seconds squared there. And so if we crunch the numbers on all of that, and our units and stuff are going to cancel out to give us meters, basically. And we should end up with 31.25 meters. That would be the height that the ball goes to, 31.25 meters. All right, let's do one more part to this, part C. Part C asks, what's the final velocity of the ball? Part C, what is the final velocity of the ball when it reaches this point right here? What's the final velocity going to be? And we kind of already mentioned this, but for problems like this, since this is a free-falling object, whatever the initial velocity was right here, uh-oh, we froze up. Whatever the initial velocity is right here, at this moment right here, if this is the same height, so at this height as the ball comes back down, the final velocity is going to be the same as whatever this initial velocity was at this height. Now, if the ball were to continue to travel, it's going to gain a little more speed. So at this point here, it's going to be moving a little faster than whatever this initial velocity was. But at this moment right here, where we're at the same height, that final velocity is going to be the same as this initial velocity, just in the opposite direction. So if my initial velocity here was positive 25 meters per second, that means the final velocity is going to be right here, negative 25 meters per second.